Okay, very good. A brief introduction. Rajesh Kumar is Interim Lab Deputy Director of the National Center for Atmospheric Research, quite famous NCAR. Um, and he focuses on socioeconomic and environmental concern around the world. A very interesting topic, as we all know. And today he will give a seminar on deterministic and probability short-term air quality forecast. So I believe you are online, and I'm going to stop sharing my screen so you can share your slides.
Yeah, thank you so much, Professor Paolo. I'm really happy to be here, and thank you so much for inviting me to give this seminar, and hopefully this will be helpful for the attendees here. Let me share my screen. Do you see my seminar, the slide in the full screen mode? Okay, awesome. So yes, as Professor Paolo said, I'm currently working at the NSF NCAR Research Applications Lab. I'm a project scientist there and the interim deputy director for the lab right now. And today I'll be talking at a high level about the deterministic and probabilistic short-term air quality predictions. Um, and I will show you some examples from the studies that I have done over the last 5 years in this space. Um, you might have already heard about this topic, but I would like to start with um, with this question: what is air pollution? Right? When we talk about air pollution, it can mean many different things for many different people. And but the definition of air pollution is it represents the presence of chemicals and particles in the atmosphere above a certain threshold that causes health hazards and damage ecosystems. So we have to keep in mind that all these chemical constituents that we call as air pollutants, they are always in the atmosphere. And some of these are necessary for our survival on Earth. For example, if we do not have ozone in the atmosphere, we will have a lot of chemical buildup in the atmosphere and it would not be possible to live on Earth. If we do not have aerosol particles in the atmosphere, we will probably not have much rain on Earth. So these chemical constituents, these are important for our survival. But the problem starts when they start exceeding a particular threshold, above which they start causing health damage to ecosystem. But recent literature is also showing us that there is no safe level of air pollution. Means if you look at some of the epidemiological studies, they would say even at the levels when these chemical constituents are below the defined safe levels, they can still have an health impact. But we have to be careful. We have to think about the balance, the roles of these chemicals in the atmosphere, and when they start causing major health impacts. So if there are thresholds, then somebody should be determining those thresholds. Then who are those bodies that determine that threshold? And so for the global applications, it is the World Health Organization who comes up with recommendations about these thresholds. And the latest air quality guidelines that were released by the World Health Organization in 2021 said that annual average PM 2.5 should not be more than 5 micrograms per meter cube. But since we are doing this course in UK, I want to tell you that in the UK, the Department of Environment, Food and Rural Affairs define these thresholds in terms of national ambient air quality standards. And these standards for maximum daily 8-hour average ozone is 100 micrograms per meter cube. And there is a condition associated with that, that this threshold should not exceed for more than 10 days in 1 year. And the 24-hour average PM 2.5 standard is 20 micrograms per meter cube. So you can see that it is 4 times more than what WHO recommends. And if you go to other countries like China, in China, the same value is 75 micrograms per meter cube. So one might question, why is it so? Why do we have, why do people living in China are more, can can bear exposure to more PM 2.5, and why people in UK cannot do that? So it's not because of that, it is because the governments are trying to make steady progress, and their ultimate goal always is the WHO air quality guideline. What they try to do is they have to balance their economic development versus mitigation of emissions. And so basically, if you look at a long-term history of air quality standards, you will see the governments lowering the standards with time because they are trying to make that progress. I'm sure you had a full lecture on the air pollution emissions. There are two types of air pollutants, and the one that are directly emitted to the atmosphere from a variety of sources, and the other ones that are formed in the atmosphere via chemical reactions. And I won't go into much details of that because I think you had a full lecture on that. But so air pollution causes huge losses in the UK. There are about 28,000 to 36,000 premature deaths, and there is economic loss of about 20 billion pounds every year. So you can see that it's a very serious problem. But is it only a problem in the UK? What about the world? It is actually a global threat. And if you look at the global numbers, about 7 million people die prematurely because of the exposure to the air pollution in the world. And a lot of these deaths occur in the developing world, where we do not have resources. Sometimes in some countries where we do not have early warning systems telling people what to do. Most of the air pollution episodes, they arrive unannounced. If you look at the impact on the crops, about 100 million tons of crop loss is lost because of exposure to ozone annually. And so we did a study in India looking at if you can save the food that you lose because of the exposure to surface ozone, you can actually feed 94 million people just by saving that food from the exposure to ozone. So there are great benefits to mitigating the air pollution emissions. How do we address this problem? And this is true for most of the phenomena that are happening in the atmosphere. So we always start with the measurements. These could be in the form of laboratory, field measurements, satellite measurements, and measurements are always the fundamental basis of our knowledge. We understand how air pollution is changing in a particular location, what are their absolute levels, what is their day-to-day variability, what is their day-to-night variability. So we build that fundamental understanding about the behavior of pollution from these measurements. The understanding that we gain, then we try to put that in the form of models. And these models can be multidimensional. There could be just zero-dimensional model, which we call as box model, which means that you just look into a box. You start with a chemical mixture, you expose it to sunlight, and then you just try to understand how this mixture is behaving. That is your box model. Then you have one-dimensional model. And the radiative transfer models are a good example of one-dimension models because you have the radiation coming through the top of the atmosphere to the surface. And how that radiation is interacting with those pollutants, that can be studied with a one-dimensional model. Then there are two-dimensional models. For example, everybody knows about the ozone hole issue, and we know that ozone hole occurred in the poles. And so at that time, two-dimensional models where we were looking at latitude as one dimension and altitude as the other dimension. And those two-dimensional models were very helpful in understanding how these CFCs are traveling from the equatorial regions towards the polar regions. And then came the three-dimensional models, which are now used for air quality predictions, etc., where we are considering latitude, longitude, and altitude as the all three space dimensions in our models. The evolution of these models have also been driven by the evolution in the computational science. So you can see that we did not have as powerful computers 50 years ago as we have today. So the computational evolution has played a big role in addition to the fundamental advances in our understanding of air pollution. So you have the measurements providing you a fundamental knowledge. Based on that knowledge, we produce the models. Then what do we do this with this information? We actually use these to support information dissemination and policy making. And this is at a very high level. Means some researchers, they spend their entire life into this box. Some researchers spend their entire life into this box. And there are people who are spending their lives into this box. So getting interaction into among these people is very, very important for solving the air pollution problem. And then once you have those policies, you go back to the measurements to understand how well those policies are working. So it's kind of a feedback loop. It's a circular thing. And we should see this as a convergence science problem and not just like measurement or modeling of air pollution problem. Um, I am spending my life into this box, and so I will tell you about the forecast, because forecast is just one application of the numerical models. Now the question is, why do we need air quality forecast? And there can be multiple reasons. The topmost reason is we want to protect public health through air quality warnings and alerts. It can be used to protect ecosystems because it can lead to temporary mitigations, the short-term temporary regulatory actions. It can also be helpful for urban planning, including monitoring network, because if the forecast is consistently telling you that this is one spot that has high pollution, you may put a monitoring network there to verify that. Medical infrastructure management, there could be a use in that. It is not being used for this purpose now, but if you know that you are going to have the next 3 days are going to be very polluted, and you have a lot of people with respiratory problems in your area, the hospitals might expect a lot of influx of new patients. And so in that case, maybe they can come up with a strategy where they can postpone non-urgent things to accommodate those patients. It could be, if we are able to protect public health through air quality warnings and alerts, it will lead to healthier population, which is going to reflect in terms of economic benefits. And then public awareness and education, which is vital for mitigation. Because if public is aware and they take individual actions to limit the emissions that they are causing, then it will lead to, it is very critical for mitigation. All right. Now, with this introduction, let me come to the topic of today's talk, deterministic and probabilistic predictions. What do we mean by deterministic and probabilistic prediction? So the deterministic prediction refers to just a single model prediction that a lot of agencies do currently. So if you follow this cross, then you see that, and the solid line associated with this cross, this single line, it is one forecast driven by one initialization time. Okay. So now we know a lot of things about the atmosphere. We know that atmosphere is a chaotic system, which means that if you perturb the initial conditions slightly, your end result can be very different. So with one simple forecast, we are not going to capture that uncertainty in the initial conditions of the atmosphere. For air quality, in addition to the initial conditions, there are a lot of other things that are important. Anthropogenic emissions, the emissions that are coming from cars, industries, households, traffic, those come with large uncertainties. So in addition to initial conditions, they cause uncertainties. On top of that, we have wildfires. Wildfires could be huge, and they are the source of the uncertainty in the wildfire emissions can be up to a factor of 30 to 100. So very, very uncertain parameters. We also have dust storms, and those emissions are very uncertain. And in addition to those, then we still do not understand air pollution very well. There are some processes that we do not understand. So basically, you can actually, in principle, can start from any of these, and it is difficult to say which one is correct and which one is not correct. So probabilistic prediction allow us to address that gap. So basically what you do is, instead of doing one single model run, you perform multiple model runs from a range of initial conditions, from a range of emission conditions that you think can be possible. And so you can see that those range evolve over time. And then when you ultimately get your forecast, you are capturing, it allows you to sample the entire uncertainty space and quantify the uncertainty of deterministic prediction. So basically, once you have this, you can play with it. You can do a ensemble mean, you can do a ensemble median, you can look at the standard deviation of these parameters, and then you use that metric to quantify the uncertainty of your forecast. Now, the higher the uncertainty, when you communicate it to a decision maker, say, for example, you are the mayor of the city and you have to make a decision. Now, you are looking at the forecast and you say, okay, today the uncertainty is less. It means I can put more confidence into the accuracy of my system, and I can make a more confident decision. If you have larger uncertainty, then you would say that, oh, I don't trust today's forecast. I have to be careful, and I have to maybe look at other sources of information that I have. Are the observations showing the same thing? Are the weather forecast providing me additional evidence that it is going to be a polluted day? So the uncertainty really allows the decision makers to evaluate the confidence they can put in their forecast. All right. Now the question is, what is a model? And a model is nothing but a simplified representation of a complex system. We try to build these models so that we can better understand those systems. What is an air quality model then? So it is again a simplified representation of complex systems amenable to analysis. Now, if you just Google the number of air pollutants that can be, or the number of chemical constituents in the atmosphere, it would be more than, it would be in thousands. But we cannot represent all 1,000 species or tens of thousand species in our three-dimensional models. So we have to come up with a very simplified representation. So a model is dividing the Earth into a set of grid boxes, like you see here on this side. Now, in each grid box, there are a lot of things happening. Now, the rooms that you are sitting in, you can consider those as grid boxes, even though some models are now using hexagonal grid boxes. So what I'm saying is not really relevant for some of the models. But for the sake of discussion, let's assume that our rooms that we are sitting in are the grid boxes of a model. Then within our room, within our grid box, we have the emissions that are happening. We have the mixing of pollutants. So from the floor of your room, the emissions are released, and then they are immediately mixed to the top of the roof. So within your room, in a modeling world, you have same concentration everywhere. And we know this, that it is not true, but this is a assumption that goes into the modeling system. So we have emissions, we have chemistry and aerosol processes happening within our room. There are meteorological conditions that drive those chemical reactions. Then there are subgrid processes. Maybe there are some parts of the room where a motion is starting from the surface, but it is not reaching the roof. That is called subgrid scale process. And so we have to parameterize that based on the information that we have on the walls and based on the information that we have at the roof and the floor. So then there is deposition happening at the roof because the mixing is also a circular process, right? And then you also have inflow because your room is not isolated from the world, right? So the winds would carry pollutants into your box and they will take pollutants out of your box. So inflow and outflow, that's why the three-dimensional, that's why 3 dimensions are needed. And the same thing in vertical is happening, right? If you are emitting something, it's not just going to stay at the top level of your box. It is going to mix with other grid boxes, and you need some type of parameterizations to do that mixing. But this is in a nutshell an air quality model. You put all these rooms together and you stack them together, and that's when you have your model where all these boxes are interacting with each other. Models, in addition to the forecasting, they are useful for many different things. You can predict past, current, and future air quality, air atmospheric composition using these models. You can explore interactions between weather and atmospheric chemistry. You can study the role of chemistry in the climate, the feedback of climate on chemistry. We know that aerosols are the largest sources of uncertainty in our climate predictions. You can use them for understanding biogeochemical processes. Models are very helpful in interpreting the observations that we do. Say, for example, you fly an aircraft in London and you sample air pollution. The observation will tell you where the air pollution is high, where the air pollution is low. But models can help you pinpoint the regions from where those emissions are coming that are sampled by the aircraft. And they are also very helpful in assessing the value of current and future observational system. So in summary, we need models to increase our understanding of atmospheric chemistry, air quality, and develop tools to provide relevant societal information. We have a large ecosystem of modeling in NCAR. We have models that range from box models, column models, LES models, to regional models, which you can operate at high resolution in a specific part of the world, to global models. And I won't go into these details because this is really not the topic for today's forecast. But at NCAR, we have been developing these models for very long time. And all our models are available to the community for free. So you can go and to our websites, you can download these models. You will find documentation and instructions on how to use these models. And if you have any questions, feel free to write to any of us. It is part of our job to support the community. So here I'm going to take a little break. Maybe I will pause for a minute to see if there is any question before I go to an air quality forecasting system development example. Okay. If there are none, then maybe we can continue with our talk. So for those who do not know about Delhi, it is the capital city of India. It is located in northern India, and the population of Delhi is close to 31 million people now. And there are about, in some parts, 20,000 people living in 1 kilometer square. So it's a very densely packed city. There are about 11 million cars in the city. And on the right here, you see the population distribution in Delhi. So you have the Yamuna River that flows through the eastern part of Delhi, but on the either side of the river, you can see the population density is very high. And this population density leads to very large anthropogenic emissions. So now you see, look at the map of the anthropogenic emission. It resembles what we see in terms of population density. So the local emissions that are happening in Delhi, those are very important for their air pollution. So they are producing a lot of air pollution themselves because of such high population density. Another source that is important, that actually becomes important during this period of the year, during October, November, is the crop residue burning that happens in the upwind states of New Delhi. So a lot of the times these winds are northwesterly, and so the smoke that is coming from these crop residue burning, it travels to New Delhi because of those winds. And then we have dust storms affecting New Delhi during the spring season, especially from April to June. So all these sources contribute to the pollution problem in Delhi. And then the problem is particularly acute from mid-October to the end of February. And so what really inspired our project here was this day in particular, 8 November 2017. It is called as Red Letter Day in the history of Delhi. On this day, the air quality index reached 999. And at that time, it was a big surprise, right? Means getting air quality index. You would see this type of air quality when you are in a wildfire plume. Otherwise, we saw these type of conditions back in 1950s in North America and Europe, which was really the start of air pollution research. So these type of conditions were really took the government by the surprise. And this is not a surprise anymore, because if you've been following the news, in Lahore, Pakistan, recently the air quality index reached up to 1900, double of this value. And you can see the conditions during 999 air quality conditions. So imagine what it would look like when the air quality index reaches 1900. So it's a big, it was a, the government of India took it very seriously, because the Indian Medical Association declared a public health emergency on that day, and they called the conditions equivalent to smoking 50 cigarettes a day. Delhi Chief Minister called the city a gas chamber. Maximum PM 2.5 concentration on this day reached 1500 micrograms per meter cube. And remember that for 24-hour average, the WHO guideline is 15 micrograms per meter cube. And the health studies estimate that a person on average loses 6.5 years of their life due to exposure to pollution in Delhi. So what the government is doing, government took it very seriously. They are expanding the air quality monitoring network in Delhi. They have set up an air quality forecasting system, and I have been fortunate to be a part of the development of that system, and I will show you some examples based on that. They have put a lot of mechanisms to disseminate this information to the public in the form of digital boards, SMS, mobile apps, websites. And they also launched a national clean air program with a target to reduce PM 2.5 pollution by 20 to 30%. And they have been making really good progress on that. All right. But I'll talk about the forecast system. So going back to the event that we had, the question is, did Delhi residents get an early warning? Because we have a forecasting system, and we failed. This slide shows you daily average PM 2.5 based on the observation and the model predictions in red. You can see that we were doing reasonably okay until this pollution episode hit us. So this tells us like, okay, the forecasting system was operating reasonably well. And this is a deterministic forecast until we have very high pollution events. So what is really happening those? Is there a way for us to address this gap? And so we had a lot of discussion about it. How can we really improve these forecasting systems? And so we kind of came up with a solution, not a solution, with an idea. And then we started a race against time to develop a new air quality early warning system. So we did it together with the Indian Institute of Tropical Meteorology, and our first conversation started in December 2017. Then we sent a proposal to the IITM, and it was a joint proposal developed by IITM and NCAR, and that was accepted immediately. And then we worked very, very hard during the next 6 months on system development and testing. And finally, we went operational in October 2018, because remember, those episodes have happened during 2017 autumn, and we needed a new system by October 2018 to inform the public. And then the system was finally operationally transitioned to IITM, and it is still running. I will show you a website where you can go and access today's forecast. So what did this new system do? So this is the same picture as from above. And this in blue, you see the prediction from our new system. This is for the same event. And now we are more closer to the observations. And during this acute air pollution episode, we were able to improve the accuracy by 200 micrograms per meter cube. But how did we do that? We actually assimilated a lot of the observation, the satellite observations that are available in near real time. So in this particular case, we took aerosol optical depth retrievals from the MODIS satellite that are available 3 hours after the overpass. And then we improved the initial conditions of the model every day before running the forecast. And so I can talk for an hour just about the process of assimilating those satellites and how those led to these improvements, but maybe that is a talk for another day. So I would also like to tell you that even though in the last slide I say it was a race against time and we were able to put the system together in 6 months, I want to acknowledge that we could do this in 6 months because of 60 years of research that happened before that. There is a lot of work that people have put into understanding the air pollution. They have developed those atmospheric science models, air quality models. They have developed data assimilation systems. So those 60 years of research is really what led the development of this type of system in 6 months. Okay, so then you have a forecasting system. You need to get those forecasts out to the public. And so if you go to our website, you wouldn't exactly find the same type of thing, but you will be able to see an animation of PM 2.5 on the website over this domain as well as over entire India now. Since then, we have expanded it to entire India. You would see the time series of PM 2.5 as a function of the forecast hour, which is actually averaged over this black box here. Now, this is the total PM 2.5. And remember, I told you that the crop residue burning is a very important parameter that is affecting air quality in Delhi. So we are also uh, producing a map of the influence of crop residue burning. And so you can see this is the carbon monoxide that is emitted by fires only. So you can see these plumes passing through the Delhi box, right? So you saw that plume that was passing through Delhi. But now on the second day, the wind direction changed and now the influence is going into Pakistan. So this thing happens that there is cross-border transport of air pollution. Means these borders are made by man, right? But these are geographically the same areas. So the crop residue burning that is happening in Pakistan, now you see the influence coming into India because the winds are that way, and this pollution plume going through Delhi. But 24 hours later, the winds change, and then the pollution from the Indian fires go into Pakistan. So this highlights the need for regional cooperation between governments to solve this problem effectively. We cannot be work just within our administrative, within our political space to solve this problem. And if you go further, you would find similar things going between India and Nepal, India and Bangladesh. And you go to any country, if you talk about Europe, you will see a lot of cross-country pollution transport there. And so regional cooperation is very, very important in mitigating this problem. All right. So we have this air quality information out. It goes out to the public, and it is now used by the Commission for Air Quality Management, who is the most powerful regulatory agency in India, appointed by the Supreme Court of India. So they take into account the air quality forecast information that we provide. And based on if there is a polluted air forecast, they put restrictions on activities. And if you follow the Indian news, you would see similar headlines most of the time, a lot of times during the winter season, where the schools are shut down, colleges are shut down, there are bans on construction activities. And then when there are cleaner air forecasts, they try to go back to the normal operation. So in the last winter itself, the CAQM, the commission used these forecasts to make this type of decision 14 times in 3 months. So these air quality forecasts are really helpful for the decision makers. Okay, I would again pause for a moment to see if there are any questions on this topic before I get into the final topic of my presentation. If not, then let's continue moving. Now, as I said, that deterministic forecasts, they are just one piece of information available to the decision makers. So probabilistic forecasts, they provide the information about the uncertainty. And we hope they provide better forecasts than the deterministic forecast. So there are two ways to do this. And so the first way is you design a dynamical ensemble. So we basically follow the picture that I showed you, where you perturb your initial conditions, you perturb your meteorological conditions, and this is kind of a high-level description of an air quality model. You have the initial and boundary conditions, you have meteorology, emissions, transport, chemistry, physics, deposition processes. That then gives you the gases and PM 2.5 predictions. Now, in our ensemble design, we only perturb these three parameters. In theory, you can perturb all of these, but then you will end up with a large number of ensemble members, which may not be computationally feasible. But so we try to capture these three sources of uncertainty. And now this is the impact of meteorological variability on PM 2.5 distribution. So this panel here on the left is the control member. The panel in the middle is one meteorological perturbation. This right panel is the another meteorological perturbation. The first row is January, the second is April, the third is July, and the fourth is October. Now, when you look at these, all these maps looks very similar to each other. It means if you ask a child to look at these maps, they would say, yeah, it's yellow and red on the eastern side, it's more blue, green on the western side, right? But when you are a scientist, you start getting into the details, you can see, oh, there is more red here than here. Oh, there is more red here compared to these two members. So this is really the meteorological variability that we are getting. And so this middle member, it showed the highest concentration in most parts of the domain in January, except for this northeastern part of the domain where the second member showed larger values. Then there is a natural seasonal cycle in these plots. So if you focus on any of these, then you would see that the concentration decrease in April and July compared to January. And this is a natural process. Even if you have the exact same amount of emissions throughout the year in your region, you are always going to have lower air pollution at the surface in summer compared to winter. And that is because of the boundary layer, because the boundary layer is very shallow during the winter. So the amount you are emitting, you are mixing that into a smaller volume. During the summer, the volume increases. And so then you are emitting that same amount of emission into a larger box. So naturally, you have higher pollution concentrations at the surface during winter compared to the summer. Then we were looking at like, okay, what are the changes in PM 2.5 because of the biogenic, fire, and secondary organic aerosol perturbations. And you see here the color scale is between -1 to 1. So you can see that over the US, where on average we have about 10 micrograms per meter cube of PM 2.5, except during wildfires and dust storms, you see that these changes are generally within ±1 to 2 micrograms per meter cube. But depending on the sources that you are perturbing, if you are perturbing like biogenic emissions, they don't have much impact during January, but they become important as you go into the summer season because the biogenic emissions, they increase with increase in temperature. When you look at these two panels in the middle, they are because of the SOA perturbation. And then you can see that, oh, okay, when the biogenic emissions becomes important, my secondary organic aerosol formation perturbations also become important. Um, the enthalpy of vaporization becomes important. And some of these perturbations are act in opposite directions. Like when you are changing the mass yields, then you are forming less SOA. But when you are changing the enthalpy of vaporization, then you are increasing the SOA throughout. So these perturbations can also act in opposite directions. When you increase the fires in the model domain, depending on where the fires are present, you get more PM 2.5. But the largest impact that we saw was because of the anthropogenic emission perturbations. And now you can see that the scale here is ±10 micrograms per meter cube. So in our study, this was a specific study. This conclusion should not be generalized. And anthropogenic emissions led to largest changes in PM 2.5 across corners. Now we are trying to do the same study, but focusing more on the wildfires. And then we are finding more uncertainties because of the wildfire emissions over the western half of the US. But then you have to evaluate these predictions. So what we do is we take all the observations that are available over the US. This is just showing correlation coefficient, spatial distribution at all the sites in the US with our ARWP2 member. And here it is very interesting to see that the eastern half of the US shows very high correlation, where things are driven by anthropogenic emissions. And the western half of the US shows lower correlation. And this is consistent across the members because wildfires play a very big role in the western half of the US. And those are very, very uncertain processes. Then what we do is we divide these observations as a function of EPA regions. So you can see there are 10 EPA regions defined by the US Environmental Protection Agency. And then we look at the model performance there. Now here what you see is in black, we have the daily average PM 2.5, and we are looking at all the 10 regions. In red, you have an ensemble mean based on our members that I just showed you, that are based on meteorological perturbations, the emission perturbations, the SOA perturbations. Now, what is where, and in blue, we have the calibrated ensemble because as I showed in the figure previously, we did not capture all the sources of uncertainty. We need some type of calibration. And then there could be one lecture itself on calibration techniques for this ensemble. But for now, let us just assume that the red is purely based on model predictions. Blue is combining information from the model and observations. What was very interesting is in the first 6 regions of the US, coming back here, so 1, 2, 3, 4, 5, 6. So mostly Eastern US, where we have very high correlation. Your raw ensemble prediction and the calibrated ensemble predictions are very similar, which means that ensemble prediction itself are very, very helpful in getting the PM 2.5 over Eastern US. When you go to the regions 8, 9, and 10, even in region 7, because that is the region 7 is also a part of that half where the model show high correlation. But when you go to 8, 9, and 10, which are Western US and are affected by the fires, the ensemble that we had substantially underestimated the observed concentration. And we could not get a better prediction of PM 2.5 unless we calibrated the ensemble, unless we bring the model and measurements together. So this is similar concept to data assimilation. You are trying to constrain the model with the observations, right? So the model measurement fusion, it is a very, very important aspect of air quality forecasting. It may not lead to an immediate advancement of science, but it can lead to much better air quality predictions. And then we compared the performance of our calibrated and raw ensemble member with all other ensemble members. So you see here, the first column here is as a function of the EPA regions is the calibrated ensemble member. It is the most red, which means we have the best performance here. You look at the mean bias, you have the least, or you have the kind of whitish or light blue colors, which shows the best performance. And here you have the least root mean square errors in your calibrated ensemble. So that's why ensemble predictions are generally more accurate compared to the individual predictions. But these are very, very expensive. We ran a 24-member ensemble. And when people are doing operations, they might not have those type of resources. So there is also an alternative technique, which we call as analog ensemble. And in this one, what we try to do is we do only one model prediction as a function of time. We make a 24-hour PM 2.5 prediction. And then we go back into the forecast space and we try to find analogous conditions that have happened in the past based on temperature, based on meteorology and chemistry. Then we take observations corresponding to those analogous forecasts. And then we make an ensemble based on those observations that are identified based on the analogous conditions in the forecast space. Now, this with this technique, this is computationally very efficient, but you can still end up with a ensemble prediction. And so here I'm showing two examples at one station, like how does PM 2.5 behave, how does ozone behave. And so you can see the observation in black, model prediction, the deterministic prediction in red. And you can clearly see that we are missing these peaks. And then our analog ensemble mean is in yellow, the dashed line. And then the variance of the ensemble in the purple color. So you can see that the variance tells us that there is a probability of having a high pollution episode, even if it is not captured by the ensemble mean or the deterministic prediction. And that's where these type of predictions can be helpful. Look at ozone. If you look at red, look at the nighttime over prediction. And this is a long-standing common problem in air quality models because we do not understand the nighttime boundary layer very well, the stratification that happens, and our models are not able to capture the nighttime boundary layer very well. So there are usually errors in the ozone titration in the models. And with the analog ensemble, because it's an ensemble based on observation, we eliminate that error. So again, we improve the accuracy. Maybe we are not advancing the model, but we are improving the accuracy. And that is what a decision maker cares about. If you look at the bias, we reduce the bias in PM 2.5 by about 95% and in ozone by about 85%. So there are different ways to provide this information to the decision makers, to provide the deterministic forecast, to quantify the uncertainty associated with it. So with this brings me to my summary slide. Air pollution is one of the most important environmental problems facing the society. The last 60 or 70 years of research, we have really developed capabilities to predict this pollution 3 to 5 days in advance. And I call this as a revolution because if you go into the history, and you will realize that it took scientists 30 years just to understand what is the chemical formula of ozone, right? When people had that pungent smell smelled in their laboratories and they started to understand what is the compound that is causing the smell, right? There is a whole history. People came up with the name ozone, right? Which meant that smell. People came up with a theory that, okay, if the smell is only in the lab and not outside the lab, there must be something that is killing that particle, that gas. And people came up with the theory of anti-ozone, which was then later proved to be wrong, right? So it really took the community 30 years just to understand that the molecule that is causing the pungent smell is O3. And now we are here in an era where we are basing ourselves on centuries of knowledge. And using that centuries of fundamental knowledge, within 60 years, we come from a situation where we had no idea about the air pollution. When the first smog episode hit Los Angeles in 1940s, people thought it's a chemical attack by Japanese because that was the time of World War II, right? So we have come a long way within those 60, 70 years. We have come from a situation where we did not know what the air pollution is. And today we are able to predict what the air pollution will be in 2100. To me, it's no short of a revolution. So we really have the capabilities now to predict air pollution in advance so that we can help the decision makers protect the public health. And so both deterministic and probabilistic predictions are very, very valuable for the decision makers. So with this, I would like to thank you, and maybe we can have spare 10 minutes for questions.